Like any design, the problem to be solved must be defined. In the case of a cam follower system, we need to know what the output requirements are. That is, what is the follower supposed to do, and when is it supposed to do that? A timing diagram is used to define those things. Here we have an Excel spreadsheet where we can define cam position and follower displacement. We'll just use this for a simple rise, dwell, fall cam. We'll start off with 0 position of the cam and 0 position of the follower. We then go to 90 degrees for cam position, and we'll just use 1 inch for the follower displacement. It's going to dwell, so it's going to stay at 180 degrees cam position, and the follower will still be at 1. We'll go to 270 degrees, and we'll bring the follower back to 0, and then 360 degrees, and we're still at 0. This is defining one of the cams. You can then go to cam 2, 3, 4, and 5, and even extend that to other cams to have a timing diagram for the entire cam shaft. In the timing diagram, all we have to show the motion are straight lines for the displacement rise and displacement fall. The next question is, what kind of motions do we want for these portions of rise and fall? This can be answered by looking into the available motions. In Cam Designer SE, there are the following motions available: cycloid, harmonic, constant velocity, constant acceleration, modified sine, modified trapezoid, modified sine with a portion of the segment being constant velocity, modified trapezoid with a portion of the segment being constant velocity, polynomial, which can be made to do just about anything you want to do. And if you want the follower to move in one direction and immediately turn around and go back in the other direction without pausing, there's a rise return. The best way to decide which of these motions should be used is to look at their properties. In the online or local help, there's a page for each one of these profiles. Let's just look at a couple of those to see what the main properties are for these profiles. For the cycloid, we have a graph that is a normalized graph going from 0 to 1 for the cam position and going from 0 to 1 on the displacement. And the displacement is always positive on these graphs. You can see that this is a sine curve for the acceleration. It goes from 0 acceleration to maximum at 1/4 or 25% of the segment. It goes back through 0 at half or 50% of the segment. It is minimum at 75% and back to 0 at 100%. This profile is symmetrical about the 50% point. And you can see that the velocity curve has a 0 slope at 0%, 50%, and 100%. Also, the displacement has a 0 slope at 0 and 100%. The harmonic, or cosine acceleration, you can see that the acceleration goes from maximum at 0 to minimum at 1. There's an instantaneous change in the acceleration at the beginning and at the end. There's also, for the velocity, there's a slope at the beginning and end. It does not go to 0 slope, but there's a slope because the acceleration is non-zero. We have a 0 slope for the velocity at the midpoint, or 50%, and also you can see that there is zero slope for displacement at beginning and end. The constant velocity profile is a very simple profile with just the velocity being constant and the displacement is a ramp. One thing about this, though, is you have to have something to accelerate the follower to that value of velocity, and you have to have something to decelerate that from that value of velocity back to zero. And this curve, like the cycloid, is symmetrical about the 50% point. The constant acceleration has a ramp for the velocity and a power curve for the displacement. Now, unlike the constant velocity, you can immediately accelerate to this constant value of acceleration and decelerate immediately from that. However, that's not recommended. One of the most used profiles is a combination of cycloid and harmonic. With the cycloid, if you recall, it has a larger maximum acceleration than the harmonic. But the harmonic goes from zero to this maximum acceleration immediately, while the acceleration for the cycloid is over the course of that sine curve. So to mitigate these two problems, with maximum acceleration being too high for cycloid and the immediate acceleration to maximum for the harmonic, we combine the two, cycloid and harmonic. We use the first 1/4 of the cycloid to accelerate to this maximum acceleration for the harmonic, and then blend it with the harmonic between that and the 7/8 portion of this segment, and the last eighth is the last quarter of the cycloid going back to zero. For the de facto standard modified sine, 1/4 of the entire segment is cycloid. 1/8 at the beginning is the acceleration portion of the cycloid, and the last 1/8 at the end is the deceleration portion of the cycloid. And then 3/4 of this segment is made up of harmonic. CAM Designer SE uses what is known as a C factor. And the C factor for the standard modified sine, in quotes, is a C factor of 0.25, which, just like I said, is 1/4 of the entire segment, being 1/8 of it at the beginning, 1/8 of it at the end. Sometimes it's beneficial to use a constant velocity portion in the middle of a modified sine. This we have as a modified sine x% CV. You can change that x% from 0 to 100%. I wouldn't recommend 100%, but you can make that, and sometimes about 50% makes a very smooth profile. Modified trapezoid is a combination of cycloid and constant acceleration, constant deceleration. We start off with 1/4 of the cycloid to accelerate to the constant acceleration. Then we use the from 1/4 to 3/4 of the cycloid to go from the constant accel to constant decel, and then the last 1/4 of the cycloid to go back to zero. The properties of this are, at the beginning and end of the velocity, we have a zero slope, and in the middle we have a zero slope. Also, for the displacement, we have a zero slope at beginning and end. And in the middle, where the constant acceleration is and constant deceleration is, we have a ramp for the velocity. Similar to the modified sine x% CV, we have a modified trapezoid x% CV. where you can specify a portion of the segment to be a constant velocity. The graphs shown here are for the polynomial. And you can see that the polynomial can be made to do just about anything you want it to do. The top graph shows constraints for acceleration of 0 at beginning and end, velocity of 0 for beginning and end, and displacement 0 at beginning and some non-zero value for the ending. In the bottom graph, we have 0 specified for displacement, velocity, acceleration, and jerk. At both beginning and end for acceleration, velocity, and jerk is 0 at beginning and end, but displacement is 0 at beginning and some non-zero value at the ending. You can see the top curve is very similar to the cycloid. The bottom curve is like the cycloid, except the acceleration has 0 slope at beginning and end. Sometimes it's necessary to move out to a certain point and immediately return. The rise return is the profile to use in that case. You can see that from the graph that we're using modified sine and harmonic together here. At the midpoint of this, where the rise immediately returns, the displacement immediately returns, we are matching all of these parameters: displacement, velocity, acceleration, and jerk. This makes a very, very smooth profile if you need to move out and immediately return. Now, how do we use these various profiles that we have? How do we combine these to get the most out of our CAM design? That will be covered in another video.